talk about finding key features of rational functions. And we talked a bunch about key features beginning of the week. Rational functions, they've got 5 main key features that we're going to go over and we're going to hunt for. And we're going to be doing this algebraically, meaning we're going to use the equation and do some algebra to find exact spots of these things so we know where they fall. So first off, before we get into that, which expression from this rational function is the numerator? Where's the numerator in a fraction? It's top, right? So the numerator, I'm going to highlight it in yellow, is the top. The denominator is the bottom. And instead of just being numbers in this thing for a rational function, we're going to have x's at least in the bottom to make it a rational function, sometimes in the top. Okay. Now we're going to talk about this term degree, because we're going to use this to help us figure out the asymptotes. But when we talk about degree of the numerator. So the numerator is the yellow one. Degree is the biggest power in the polynomial that's on the top. So the biggest power in the polynomial on the top is 3. So what we would say is that the top, the numerator, is a third degree. So with that same knowledge, what's the degree of the denominator then? Does it have a power? Ooh, yeah, it does. What number can be written with x that we don't ever think about because it doesn't do anything? 1. It's linear, but it does technically have a degree, okay? So this is a first degree polynomial. For what value of x will this function not be valid or be undefined? So when we look at this, I'm going to erase what we've got up here. We're looking at this fraction. What this is asking, what number can I not use for x? Because I'm not going to be able to calculate it. So there's only really 2 things that we can't do, that we can't get real number answers for. One of them has to do with the square root, which isn't this one, and the other one has to do with fractions, because fractions are dividing. What can we never divide by? 0. So based on that knowledge, what number can I not pick for x? Because I'll get division by 0 on the bottom. If I made this x one specific number, what would make it equal to 0? When x is 3. 3 minus 3 is 0. That's the one value that I can't use in this function because it'll give me division by 0, and division by 0 is bad. I'm not going to worry about graphing it for this one, but you can look at the graph and you can start seeing some of the things where these pieces fall. But I think some of you have worked on some of this already, so we're going to talk about the actual features of this thing, okay? So we're going to use degree. We're going to talk about where it's not defined. You know, we got to know which one's the numerator, the denominator as we go through. But I gave you this list with these 5 key features defined. We got to find holes, vertical and horizontal asymptotes, x and y intercepts. Those are the 5 key features that I want you to be able to track down for all these rational functions. Now, when we deal with holes, this says to set any factor that cancels equal to 0. Those are your holes, which word-wise doesn't mean a lot until we actually do this. Now, I'm going to attack this a little bit better when we get into an actual problem where we see this happen. But whenever you have a fraction, what do you have to do first to all your fractions? Like, let's do it with just numbers to talk about this. Would you ever write 6 over 8? Would you leave 6 over 8? What would you do? You would write 3 over 4, right? Because you would cancel out the common factor of 2 out of this thing. That's what I'm talking about here. When we go through and we look at our rational functions, which have polynomials in top and bottom, we got to look and see if anything cancels out of the top and the bottom and simplify it first. which is going to require us to do some factoring. If something cancels out, we're going to use that to find our holes. Vertical asymptotes. Which way is vertical? Up and down or left and right? Up and down. So these are our up and down asymptotes. Remember, those are our dotted imaginary lines that our graph tries to cross but can't. And when we go to find these, it says after finding any holes, you see what's left in the denominator and set it equal to 0. And that will tell us where this vertical asymptote is going to go. Meaning, we come back to this one, this x can't equal 3. This is actually where my imaginary vertical line would be in this graph. That asymptote would fall at x equals 3. Horizontal asymptotes. Which way is horizontal? Left and right. Now this one is a little bit trickier, and we don't actually learn all of this one because we haven't learned one of the mathematical operations we need to find this, but this can come in a couple different flavors. Okay? You can have a horizontal asymptote that goes straight across, or you can have one that's called slant, which means it's like a line still, but it's tilted one way or the other. It has some slope to it. Or even more extreme is sometimes you can get polynomials as asymptotes. And we don't get into any of that finding until we recover this again in pre-cal, but it helps to understand that it comes in three different types, but it's the same thing. What we're going to be doing to find horizontal asymptotes, we're going to be comparing degrees of the numerator and denominator. And then there's going to be sets of rules to help us find our answer for this at this point. So we're going to compare the degree of the numerator and the denominator. We're going to say the numerator is bigger than the denominator. If the degree of the numerator is bigger than the denominator, our answer at this point is going to be that this is a slant or polynomial asymptote. It doesn't have a true horizontal, meaning you're not going to find an equation, you're not going to have anything yet because we don't have all the tools necessary to graph that quite yet. I'll show you eventually how to do it, but we've got to learn some more stuff that we're going to learn later on, okay? If the degree of the denominator, so the bottom is bigger than the top, degree of the denominator is higher than the numerator, bottom bigger than the top, your answer for your asymptote is always y equals 0. And that's an equation of a line. Meaning when we say y equals 0, and we look at it on the coordinate plane, that's an equation of a line at y equals 0, which means that, I'm going to try to make this stand out a little bit. The asymptote actually falls on the x-axis. That would be where our dividing line is for that one. Okay? That's a y equals 0. It's a line that goes through the y-axis at 0 all the way across forever, both directions, negative infinity and positive infinity. Last one, degree of the numerator and denominator are equal, meaning they'd have the same biggest power. This one's a tricky one for us. We're going to get an equation of a line still, y equals some number, but we're going to have to take the coefficients of a and b from the biggest term in that polynomial and divide them. And until we get one where I can show you this set of notes probably won't make a lot of sense. But we're still going to get y equals a number like we did here, but it's not going to be 0. It could be something like 2, -5. It'll move this thing up or down where that horizontal dividing line is. X and Y intercepts. So let's talk, and really this shouldn't say intercepts. This should say intercept, because you're only ever going to have one of these. You're going to put a 0 into your equation wherever you see an x and solve for y. And it'll tell us the x value of, sorry, the y value of our y-intercept. And then we're going to do the same thing for the x-intercept. And all of these things are after finding holes. That's what's left in the numerator equal to 0, solve. That's the x-intercept. Now a lot of these notes, I think we can kind of see where they're going, But until we see one in actual example, sometimes they don't make a lot of sense. So I'm going to be flipping back and forth between this one, and we're going to do this example. So what I want you guys to do real fast, write down this. Don't worry about writing down these answers yet. Write down this rational function, and we're going to do that one together right now. So what I personally feel makes this a tougher topic for everybody. You have to factor to be able to do this. And what do I mean factor? I mean common factor, A times C factoring. We got to factor this bottom quadratic. We've got to factor the common factor out of this, and we've got to look for anything that cancels first. So you've got to be able to factor these first. So what happens here? Let's talk about the numerator. What's the common factor in the numerator? 3x and minus 3 have a 3 in common. So I can write that as 3x minus 1. Because what I'm doing by factoring is I'm looking for something to cancel, because this is where I'm hunting down what the wholes are. Now I need to factor x squared minus 6x plus 5. So I know that's going to be that, because I'm doing box factoring. The x squared goes here, the positive 5 goes here, and since I have 5 times 1, I'm looking for the factors of 5 that equal negative 6 when you add them together to fill in the other two corners of the box. So that's negative 1 and negative 5, because when you add those together, you get negative 6. So that means this was negative 1x, this was negative 5x. Then we do our common factoring. Those were the two things we multiplied together to get to that quadratic. So you're going to have to be able, you're going to have to review your factoring to make this really go through this process. And I'm pretty sure I have a decent video on factoring I'll send out to you guys this afternoon. Might help you if you need to review that. Now, the reason we needed to factor all this stuff, this is still a fraction. All these things are multiplying. Something's going to cancel out now. What cancels out? This whole term, x minus 1. Anything in the same top and bottom of our fraction is going to cancel. So that means we only have 3 x minus 5 left. This is the same thing as that with the common factor factored out. It removes the whole. So when we go through and we start dealing with all of our features, the first one we always have to deal with is finding any holes. What did I cancel out? I canceled out the x minus 1. So what this says right here is set anything that cancels out, any factor that cancels out equal to 0, and it'll show you where the hole is. Now the hole is a point, so we got to find its x and its y, but x minus 1 canceled out. To find the x value of the hole, I set that equal to 0, and I solve. So that tells me that its x value is 1. How do I find the y value though? And that's where our function comes in handy, because what we've done is we've simplified this out. You have to remember that when you have an equation, it takes X inputs in and tells you the Y that goes with them, which is we want the Y that goes with it. So we're going to take what's left over, and we're going to put this 1 in here on the bottom so we can figure out what the Y value of the whole is as well. So 1 minus 5 is -3/4. So that means the Y value of our whole is -3/4. And I'll show you when we graph this one on Desmos what we see there. But what happens is it's almost like somebody takes a hole punch right at that specific spot, punches a hole in our graph. So that's how we find the holes of our functions. You always want to do holes first. Do you always have to have a hole in your rational function? No. You could factor these things and nothing could cancel out. If nothing cancels out, then the answer for holes, if you're asked for it, is none. The only time we have a hole is when we see something cancel out, like we did with this X minus 1. So now we need to deal with the rest of these. My suggestion as you go through this process is to pick a pattern of the way that you solve these things and do it the same each time. Like if you start with holes, which you have to, then you do horizontal asymptotes. Always do horizontal asymptotes second every time. Then always do vertical, do it in the same order every time, kind of like muscle memory. It'll be a little bit easier because it's a lot of information that's getting thrown together. And as you practice this more, you'll start going quicker. And if you flip around the order on yourself, you might have some issues. So let's find the horizontal asymptote because it's next on my list. It really doesn't matter after holes which order you do this stuff in. But like I said, I suggest you kind of pick a pattern and stick with it. So horizontal asymptotes. We're going to go here and read our notes on this. Horizontal asymptotes are the ones that we are comparing the degree of the numerator and denominator. So I need to look at my fraction and list the degree of each. And to do this, I need to go back to the original. What is the degree of the numerator, the 3x minus 3? The degree of this thing is 1. So it's a first degree polynomial. The degree of the bottom, biggest power we have is 2. That makes this a second degree polynomial. And this is where we've got to take this information and read our notes on this to figure out what type of answer we're going to have. So right here says the degree of the numerator is higher than the denominator. So the top is bigger than the bottom. Is the top bigger than the bottom? No. The degree of the denominator is higher than the numerator. So this is the bottom is bigger than the top. Is the bottom bigger than the top? So this is what we have for this one. That means our answer for this asymptote is y equals 0. So y equals 0 is going to be the equation of the horizontal asymptote. Let's do vertical asymptotes next. So let's jump back over to our notes. Vertical asymptotes. It says, after finding holes, see what is left in the denominator. It should be a comma. Set it equal to 0 and solve. So this is where we found our holes. This is what's left. This is the important part of this, what we'll work with most of the time. You want to work with the fraction after you factored it. So what's left in the denominator? X minus 5. So we know that we have x minus 5 here. And it says to set that equal to 0 and solve. So what makes x minus 5 equal to 0? Well, we add the 5 to both sides, and we get x equals 5. This is the equation of a vertical line, goes through x at 5, and that's where that asymptote, that dotted line is on our graph. So now x-intercepts and y-intercepts. Always deal with what's left over. And we're going to tackle this. We're going to do y-intercepts next because it's just next in my list. Now, one of the key things we talked about, this key feature, if you're on the y-axis, you already know one value of your coordinate for your answer. You know, if you're on the y-axis, what does your x have to be? Your x has to be 0. You know that for fact when you start. So what we do is we make the x in here 0 to figure out what the y is. So to figure out what the y-intercept is, we're going to plug in that 0 for x and evaluate what's left over here. So this is 3 over -5. You can leave these things as fractions. If they come out as nice decimals, like 0.25 and 0.4 and stuff, you can obviously do that. Or you could just as easily write the -3/5 in there. It's -0.6, but either way is fine. The only thing I ask you not to do for wholes and asymptotes and intercepts is don't round them. If you get something like divided by 3 that's going to repeat forever, write it as a fraction when you write your answer. So that is our y-intercept. One more to go, x-intercept. You know what the y value has to be. The y value has to be 0 for you to be on the x-axis. So we're going to use that in our equation to figure out where this thing crosses. So we're going to make our y value over here 0. So 0 equals 3 over x minus 5. Now this is a little bit confusing at first. How do you get rid of the x minus 5 in the bottom? Let's think algebraically. What would we do to anything we have a denominator for? We don't want it there. We would multiply by x minus 5, right? So that this cancels, which means this gets multiplied by x minus 5. What is, well, hold on, let me get rid of the red ink here. When this cancels, we know that this answer is 3. What is x minus 5 times 0? What's anything times 0? You know, 22 million times 0 is still 0. Any complex polynomial times 0 is still 0. So this one actually gives us a weird result. Does 0 equal 3? Whenever you get an expression like this that gives you something that doesn't work, you're not going to get an answer for it. This means that we don't have an x-intercept. We would get something, x equals a number, like we did y equals a number down here to fill in that spot. But since we get the x disappears, it doesn't work. We don't have an x-intercept. And we'll see when we sketch a graph for this why that makes sense, okay? So I'm actually going to sketch this one before we move on to Desmos with it and kind of look at it there. Because overall, I want you guys to be able to put this information onto a graph. So let's see, we should be. So let's start putting this information on our sketch so we can get an idea what this thing looks like. So the first thing that I want you to put on these every time are the asymptotes. The asymptotes are dotted lines, and I'm going to make mine a different color, and I'm going to leave it dashed, okay? It's not really part of the graph. It's kind of like if you're making a perspective sketch in art, where you get the angled lines so you can kind of get all the sizes set up so you can see things in the back are smaller than the things in the front, you get everything in the right face. It's kind of like those. They're not really part of the sketch, but they make it work and make us understand how to draw everything. So the first one is at y equals 0. y equals 0 lines, and now this is horizontal, it's going to go this way through y at 0. So this asymptote is right here. And I'm going to make this line a little bit bigger so we can see it. Now that means that, now remember, rational functions have two pieces. Those are two L graphs. One L is going to be above that green line. The other one's going to be below it. They're never going to touch each other. That's its dividing line. The other one is at x equals 5. I'm going to put that one in a different color. 1, 2, 3, 4, 5 on the x, and it's vertical, so it goes up and down. At 5 on the x. Oops. Now what we've done, I want you to think of this. We've actually sectioned this off. If you remember our rational functions, and I'm just going to draw a basic sketch from our function families stuff. We saw that when we looked at this, there were two L's, usually like that, right? And they moved around based on the equation, but now you can kind of see, if you look at these two asymptotes, they take those L shapes are in the corners of these things. And there's two asymptotes that can't pass, meaning there could be an L shape up here and over here, or one over here and here. But it's breaking down and showing you where those things go. Now, when you put this on your sketch, make sure you label these. This is at y equals 0, and this is at x equals 5. So we put this and this on our graph. Now we've just got to figure out, we know that there's going to be, don't draw this on your graph if you're following along with me. We know there's going to be an L somewhere in one part of these. We just don't know exactly where it's going to be yet. That's where the points come in. So let's go through and put our hole in. It's at 1, -3/4. So I'm going to put these in red. So it's at 1, -3/4. Now it's a hole. And I want you to think holes are like hole punched. Those are our open circles. Think about the interval notation stuff we've talked about. So I'm going to draw an open circle right here. I know it's a little bit big. It's not perfect. This is a sketch. Okay, that should be a little bit above the -1, but it's pretty close. So put that on there. The y-intercept is at 0, -3/5. Well, 0 and down, so that's like down 0.6. That puts it right here. Do I have any x-intercepts to graph? No, I don't have any. So this is all the information that I gathered. So what does this graph look like? Well, we know it has these two L shapes, okay? We know since there's 2 points in this corner, and it's going to take me a second to get this graph looking good. One of them is over here. Where's the other one? We know it's got to have another one, and if you look back at some of the ones we've done, it's most likely up here. They're usually in opposite corners of each other. But what I'd like you to do, just real quick, to find this other point, since all of the information we found was in one corner, well, we want to test to see where the point is over here. So pick an x value that's past 5. How about x equals 6? What happens when you plug 6 in here? What do you get as an answer for your y? If we go y equals 3/6 minus 5, it tells me that y should be 3/1 or 3. So it means that the coordinate that I found over here at x equals 6 is 6, 3. Let's graph that point and see where it is. So there's 6, there's 3. It is in that corner. Once you get a point in one of these corners, you'll know that your L-shaped graph goes in there. You're not looking for perfection. We're looking to make sure we have the same basic shape. And I did a really bad job about getting that not crossing the asymptotes. but that's what we're looking for the information. Finding the information is going to be the key stuff for us, but seeing how it all goes together on your graph, because you could graph that in Desmos and you could actually sketch these lines out and see these dotted lines separating the graph. If you went and highlighted the graph on the left side, took it over to x equals 1, it would say undefined at that point because there's a hole there, but that's finding that information. Try another one? I think we'd try another one. So using that bit of information, all right, so there's my answers. So biggest caveat with this, okay? And it's really easy because we hadn't directly practiced it a lot. If you don't factor the first thing right in the beginning, what happens to everything after it? It becomes wrong, right? So you've got to be really, really cautious. I didn't draw the boxes on this one. Guys, do whatever you need to do to factor that one correctly, okay? But the top one factors into x minus 3x plus 2. The bottom one factors into x plus 4, x minus 3. And you get a x minus 3 that cancels out. So this x minus 3 that cancels out x minus 3 that canceled out up here is what we use to find the x value of the whole. Now this is also important, and I don't want to skip over this. This equation right here, once we've simplified it, is what we're going to use to find x-intercepts, y-intercepts, and the vertical asymptote. And it's going to be easier to deal with because if something canceled out of it, it makes the math shorter. So once you find out what cancels, now you don't have to have something that cancels every time. I'm putting our examples with stuff in them every time so that we see each part getting worked. But if something doesn't cancel out when you go to factor, it just means that you have no holes. You can have an answer that is none for holes. You can also have answers that are none for y-intercept and x-intercept, okay? So we take the x minus 3, set it equal to 0. It tells me that the x value of my hole is 3. Now to find that y value that I found over here, we take what's left, we plug the 3 in where we see an x. So this is now 3, so the y for this is going to be 3 plus 2 divided by 3 plus 4. 3 plus 2 is 5 over 7. 5/7 is the y position for that hole. So all of this stuff in here is about finding a hole. Then I went through and I looked at horizontal asymptote. Now remember, horizontal asymptote is where you compare the degrees. So the degree of these things, they're both second degree, which is the same. So if we jump back to the notes, for ones that are the same, here it is, degree of the numerator and denominator are equal. It tells me that the equation can be found doing this with this weird a and b coefficients. What are coefficients? Coefficients are numbers that are in front of an expression. The coefficients that you're looking for are here. They're the numbers in front of the term you pulled the degree off of. What numbers are really there, even though they're not written? Both of these numbers have a 1 in front of them that we don't write. That's where I got this 1 divided by 1, which is 1. And this is an equation, which is why I leave it as y equals. So that is the equation of the horizontal asymptote. You'll see a line, you have an imaginary dotted line going through the y-axis at 1 that cuts the graph in half top to bottom. So you know where the top half would be above it and the bottom half would be below it. Vertical asymptotes. You've got to go back to this thing that we had in green after we factored. Vertical asymptote said to take the expression on the bottom, which is x plus 4, and set it equal to 0 and solve. So x plus 4 equal to 0. If I want to solve for x, minus 4 from both sides. The equation of the vertical line, it cuts my graph in half left and right, is at -4. So remember that this is a equation of a line. So at -4, that would where the left side and the right side split would be. Now, x and y intercepts. We're using the same methodology to solve for both of these things. Let's start with the y-intercept. To be a y-intercept, I know that my x value must be 0. I need to figure out the number to put in here for the y. So what I do is I take the equation that was left over here in green and I substitute in 0 wherever I see an x, and then calculate my answer. So 0 plus 2 is 2. 0 plus 4 is 4. So 2 over 4 simplifies into a 1, or into 1/2. And that's where I got the 1/2 that goes in as the y value of that coordinate. Because remember, y-intercepts are coordinates. We need an x value and a y value. You'll know the x value because it has to be 0. You use that fact to plug into the equation that was left over to find the y value that goes in there. Now we're going to do the same thing with the x-intercept. To be on the x-axis, your y has to be 0. But y is over here, so I'm going to plug that in here and make the y 0. But this one gets a little bit weird because you have a fraction over here. Well, to get rid of that fraction, you always have to multiply by whatever's in the denominator. It's going to cancel out over here. But what is 0 times anything? It's always 0. So 0 times x plus 4 is still 0. The bottom doesn't matter in this. That's why the notes say just look at the top. Whatever the denominator is, it's always just going to kind of go away. You only need to set the top equal to 0. Then you get x plus 2 equals 0. We'll solve that. We get a -2. And the -2 is the x value that goes in that coordinate that tells me where the x-intercept is. Now remember, you can have more than one x-intercept. Most of ours will probably stick with one to start, okay? But it is possible.